I'm Brian Johnson. I'm a solutions architect in the Ethernet products group at Intel, and I'm going to kick off the first presentation talking a little bit more about ADQ. Legal disclaimer slide back then. So just to summarize, we've talked a little bit about ADQ at the last three sessions, and I put the links up here. Back in April when we were part of the data-centric launch. And then also back in October, we went over some of the ADQ and DDP technologies. In the next hour and a half, we're going to go through more detail and actually start providing some of the links to the resources that are now available. So just to summarize where the 800 series, what it is and where it fits, we have our 500 series that was out, the 82599 network controller. Also, you'll see the code name was Niantic. We have the X520, which is based off that, is the 10 gig adapter. And we introduced SRLV. We had a fixed pipeline on it, and it was really designed to kickstart the virtualization transition. As we moved into the 700 series, the primary controller there was Fortville, and that series moved mostly away from a fixed pipeline to a partially programmable pipeline, which allowed us to do more with the same controller without having to actually spin the silicon. We introduced a new concept of the Intel Ethernet adapted virtual function, and that is the same virtual function driver and compatibility that we have moving into the 800 series. So the 800 series, code name of the primary controller there is Columbiaville, introduces more features. We have the three that we're going to discuss today: ADQ, the dynamic device personalization, or DDP, and then Fred and Dave are going to talk about the RDMA and NVMe over Fabric capabilities. And with this, we have more, not just more features, but we increase the speed and the flexibility of the part, which allows us to have the same controller, and actually in some cases in our 100 gig part, all the way from 10 gig to 100 gig with the same controller. So now that we've kind of done the summary of the 800 series, and if you do want more information, the links to the other presentations that we did back in April and in October have more details on the controller itself. So as we talked about in the previous ADQ discussions, the application device queue, the idea behind why we came up with this is really to address this, the application response time and how that can impact the overall performance of being able to scale out across a number of servers. So as you add servers, that predictability and the tail latency needs to stay within check in order to be able to keep growing and maintaining your SLA. So we covered that, and we wanted to provide some updates on what's happened since we last spoke in October. So what we started out with is looking at what are some of the system inefficiencies. And these are the typical inefficiencies that most of us know and work around and work with within how the application and especially networking applications will have variability or jitter in their response times, the ability to be able to scale. And so we started digging into these, like interrupts. How do we reduce the number of interrupts? How do we stay servicing the application data longer without headline blocking other applications that may need to use that same queue. So how do we balance that out? You can read through the rest of these. As I said, these are pretty typical, but if you add all these together, it really can provide, this, the jitter, the long tails, and I have a demo and so forth to go into a little bit more detail on that. So application device queues. This is a new technology that we're introducing full support on in the 800 series controllers. And the basic premise is that we set up a set of dedicated queues that an application is tied to, that allows the application to know just its traffic is coming into those queues. So when we do that, then we can tie the application threads of execution directly to those queues, and then add some bandwidth control so we could either set a minimum or a maximum on the TX of those queues. This reduces latency, increases predictability, and can improve throughput. So you kind of think of these as expressways. You have a number of expressways that are express lanes that are dedicated to a certain destination, certain application, and you can scale that 2 lanes, 4 lanes, 1 lane, 8 lanes, 16, whatever you need for those applications. And so you separate out the traffic into those dedicated lanes, and you still can provide default lanes for general purpose traffic to go to other applications or management services. So you can see on the left-hand side, the analogy of the traffic. You have mixed traffic. When you have the mixed traffic, the queue needs to drop out of maybe polling, go make sure that another application doesn't need to be certain, that data doesn't need to go to a different application, and then it goes back. And that can cause the high interrupts, system latency. And so when we move to these dedicated queues, you can see some of the performance benefits for like memcached, Aerospike, and Redis will have significant predictability increases and reduction in latency and throughput. And as I mentioned, we'll cover the latest use of ADQ and some of our other storage technologies in the next presentation. So the basic configuration and the requirements for ADQ: one, we set up the application priority. So we use like NetPrio and C groups to direct the traffic into a set of queues. So we identify the traffic, figure out what the unique parameters of the traffic would be using TC and TC Flower. We isolate the traffic into those queues. The queue selection can be done either through standard RSS. You can do flow director or other types of traffic steering into the dedicated queues. Busy polling is then set up and allows that queue to stay up and running longer. So we know that it's only traffic for those specific queues or for those specific applications that are on those queues. So it can stay pulling that information off those queues a lot longer. We identify the queues with the NAPI ID, and then we're also providing extensions into the transmit packet steering that allows you to match the transmit queue with the receive queues for even more performance and reliability, or predictability, excuse me. We've been enabling these features since the Linux 4.12 kernel, and we're continuing to add and these patches into the kernel in order to take advantage of most of the technologies. You move up to a 4.19 kernel, and you'll be able to enable ADQ on the 800 series controllers. So with that, I'm going to jump over and show a demo of Redis. Back in April, we discussed Redis as one of our proof points, but we didn't actually show what some of the benefit was in a demo and in a lot of detail. So we'll use the demo to kind of walk through that. So as you see on the screen, up in the upper left-hand corner here, we have the average latency. On the right-hand side, we have our combined transactions per second. So this is the request rate that shows with the different number of transactions. In this case, we have 2,200 connections, and you can see the transaction rates. And then down in the bottom left-hand corner, we have the 99% tile of what number of transactions were completed within what time frame. So if we start by looking up in the transactions per second, obviously ADQ, being the blue line, has a transaction benefit. So we have almost double. And so you might think, well, I just need more servers or more connections in order to bring that baseline performance up. If we have an SLA of 100 microseconds error to stay within, obviously at 2,200, we're well within. And you can see that the jitter of the average transactions, or excuse me, the average latency, with the red line having some variability and the blue line staying pretty pretty flat. But if you look at the number of transactions that were actually completed down in the left-hand corner here, you'll see that not only is ADQ have some faster transaction completions, but they're not as widespread across this chart here. The red, starting here, moving over, has a broader spread, a little bit flatter, which means there's more variability in the number or the transaction latency. So increasing this to 4,400 connections, latency goes up slightly on the ADQ, more variability into the baseline. Transactions per second really didn't change much, but what you see is the tail on the baseline is starting to extend. So you see a much wider percentage of transactions actually being completed in the on the baseline. So if you look at the 99.9%, you'll see that we're still at 500 for the ADQ, and we're bumping up into the 900 for non-ADQ. Going to 6,600 connections. Once again, you see the variability on the baseline, which does jump over the SLA. A little bit drop in number of transactions, but the latency and the curve for ADQ, once again, is relatively narrow, where the baseline is actually over 1,000 microseconds here, and you'll see that this far right red block here actually is the number up above 1,000. But it can be really hard to see if you're just looking at your transaction rate or even the latency, the average latency. You don't see that how far that tail is on the unless you start looking at how it's distributed and so forth. And the analogy that we use for this tail is if all the transactions have to be accomplished in order to be complete, you have to look at what is the last one. If everybody has to leave on the same bus, the last person dictates when you're leaving the bus station. It doesn't matter if the first person's 2 hours early. If the last person's 2 hours late, you're still leaving 2 hours late. And so that's what we've focused on within ADQ, is really narrowing this down. And you can see that within this Redis demo here. I'm just going to pause for a second, see if there are any questions. Okay. So that was Redis. As I said, we've been working with Redis and talking about Redis for the last couple of presentations. We have been recently publishing the memcached ADQ enablement, and this is an example of the patch that went upstream to enable ADQ with memcache. And so basically what it's doing is enabling the NAPI ID to allow the transmit and to match up with the receive, and also help stay within to map the polling and drivers together, and so we can stay within the polling and transmit back and have the symmetric queuing. So relatively simple patch on to enable an application of this sort. So we have a test bed, and we ran the test of with memcache server without ADQ and with ADQ. And once again, if you look at the transactions per second, you see that the throughput is, levels out as you would expect, and you get to a certain level. But once again, this isn't the whole story. Let's look at the latency, and you see that ADQ stays nice and flat throughout the number of total connections, while at a point the baseline, that light blue line, starts to increase dramatically and become pretty erratic as you increase the number of connections. So with an SLA at 1 microsecond, you'll see that the baseline application, or the baseline test, stops at roughly 2,000 connections, where the ADQ is still within the SLA of under a microsecond, all the way up into the 4,400 connection line. So that's, go ahead.
So Brian, I'm sorry, I thought I had it for a moment, and then I thought I didn't have it, and I'm not sure, so I want to check. So in your scenario, we have lots of clients talking to a memcached server. Memcached has been configured to use ADQ, and it's the only thing running on that server? In
this case, yes. It's
so I guess what's it prioritizing its queues instead of? So what would it be fighting against traffic-wise, or where's it gaining the benefit of prioritizing its traffic queues on that interface? And this is what I may just be missing here, right? So where is the win for the memcached server by doing this, if the only thing it does is these connections anyway?
So other traffic does come in just you'll have spanning tree and LODP and different types of traffic coming in.
Right.
And so those can cause some jitter, but it allows us to stay polling longer without missing any of those other transactions. So one of the things with the ADQ testing is that we do have to look at, okay, what is the maximum? And so we don't have other workloads in these particular tests working at the same time. So the isolation aspect is random traffic that may be coming in over the wire, is one aspect that we're not having two applications. But when we do run multiple applications and stuff, then you can see that both of the prioritized applications can stay within their SLAs without stomping on each other. In something like this, being able to maintain the busy pole longer, because the traffic, there isn't something coming in to stop the traffic that is going to the application. The symmetric queuing, so mapping the NAPI ID with the TX, so mapping the TX thread and to the core that the RX is coming in on, that provides a benefit. And so there are still other aspects, and also load balancing. So we're able to not rely. We can adjust.
So it's kind of doing more than just queuing, as it were. There are some real optimizations between the application and the NIC here that you're almost optimizing the way they're talking between the application, the threads, and the NIC, as it were, in addition to controlling the way the traffic flows. Because that you raised my other concern, which was, if this is something that's settable within the application, if you have a multi-tenant VM or computer, then everyone just goes, I'm high priority. And then says,
so the when you set up the ADQ, you set it up for that particular port. So if you're dealing with a physical port, so you wouldn't necessarily be in a multi-tenant environment in that case. Excuse me. And so that would be, you would set up a number of traffic classes or priority classes for ADQ. So you could say, I want, for 8 queues for your default traffic class 1, I want 4, 8, 16, whatever the numbers are, and however many of those you want up to the 8 or 16. And so you set that up. At that point, you can set the priority as the administrator. So it is up to the administrator to do that. In a virtual environment, if you're doing this with a virtual function, the virtual function can set up the priorities, but it's limited to whatever that virtual function is. And so you can control it as an administrator and say, well, the transmit of that is X. And so it's still controlled by the administrator in a virtual function environment. Right now, this isn't really set up for going through a virtual switch. So if you're not using SRIB, it would be something that it's really not designed for a virtualized environment. There are other ways that we handle that with VMDQ and so forth.
Okay.
Does that help?
No, that does help a lot. Thank you.
And actually, as we transition over to, so it's not just about the queuing, right? The queuing gets us and actually enables us to be able to do these different, address these inefficiencies more effectively when we have the dedicated queues. And once again, we know what's going to be in there. We know what the traffic is, and we can add as much control into those queues as needed. In some instances, you may want to isolate your CPUs. In other cases, you may not. So, it's kind of like security in QoS. how much do you need? Enough to get the job done, right? You don't want to go overboard. So we have put in multiple steps. You can get really fine-tuned and, crank out some really good numbers and performance. And so when we do our testing, we look at what is it, completely optimized. What can we do? And then we look at, okay, real world scenario. What can we do? What would a person typically see if they don't do all the tweaks and everything to take it to, to the max? And that's really, I kind of look at it like, setting up a race car, depending on what kind of race you're in, depends on how much how much fine tuning. If you only have to turn left, well, that's all you have to do. Rally cars, a lot different kind of tuning. So we have that ability to kind of scale between, both aspects. So the ADQ, we have an ADQ resource center. It's out on, if you just go out to intel.com/ADQ, you'll see all the solutions briefs, blogs, white papers, and performance and details that are up there. So please feel free to go look at those. It goes into a lot more detail. In a half an hour, I just wanted to make sure we kind of keep explaining where this is and some of the different areas that we've been able to optimize since the last time we talked. And so just to kind of summarize, we are seeing significant improvements in performance with enablement of ADQ, specifically in some of the groups that we've worked, or the companies we've worked with Aerospike, Redis, memcached, and among others. And really, it's about being able to separate those, the traffic, and prioritize it into the traffic classes, or not traffic classes, but the ADQ queue groups, and then the tunings that you can do within those queue groups to increase the predictability of the applications themselves. So with that, I will see if there are any questions.
Yeah, this is Tony. I don't know if you guys are going to cover this or not, but I saw in a lot of the charts you guys are using the 810 cards, yes. And the 810 cards are dual port. Each port is 100 gig. You getting 200 gigs out of? Can you run both ports active, or is it active and bypass?
It's active standby basically. The part itself can do 100 gigs. The engine will do 100 gigs of throughput. And so yeah, the dual port is allows you to have an active standby at 100, but one of the other things that we haven't really talked about in this is the ability that card actually can do 8x10, 4x25, 2x25, or 2x50 through a software configuration. So there's a tool that you can actually run it in any of those connection speeds, and those are actual physical connection changes. So you match it up with whatever switch port you have on the other side, and so the card does 100 gig, but it also does anywhere from 10 to 100 with not just a single port of 10 gig. You can do up to 8 ports of 10 gig. So, and that is, and actually Fred has a snapshot of some of the other adapters. The dual port 100 gig is the one that we've kind of talked about, but we have a wide variety of other port configurations and form factors as well.